scalar multiplication, the dimensions of matrices, and matrix addition. Scalar multiplication, to recall, we multiplied a constant times each element in a matrix. And matrix addition, we simply added the corresponding components of each matrix. But matrix multiplication is slightly different, so we're going to go through this slowly and in detail. And the reason why we do matrix multiplication this way won't be apparent right away, but it will be in the next video. So I have two matrices defined here, A and B. A is a 3 by 2 matrix, 3 rows and 2 columns. And B is a 2 by 2 for 2 rows and 2 columns. In order to be able to multiply matrices together, these internal numbers have to be the same. So the number of columns of the first one has to equal the number of the rows of the second one. The reason for this is what I do is I take this row here and I turn it and multiply it times the first column to get my first piece. Then I'll do the same thing times the second column to get the second piece. So let's see what happens. I take 2 times 3, so that's shown here, and negative 15 times negative 1, and that's shown here. And that 2 times 3 is 6, plus 15 is 21, gives me the first term here. To get the second term in this column, I take the second row here times the first column, so negative 3 times 3 plus 8 times negative 1, and that gives me this number here. Then I do the third row times the first column, and I'm completing my first column of my answer. So 3 times 3 is 9, minus 10 gives me negative 1. Then I do the same thing to get the second column. I do the first row, second row, and third row, all times the second column. So 2 times 2 plus negative 15 times 5. 2 times 2 plus negative 15 times 5, giving me negative 71. Negative 3 and 8 times 2 and 5 are shown here. That gives me the piece over here. So it's to get the element in, for example, this spot here, I would use the second row times the first column, and so forth to fill out my matrix. So all the details are shown here, and that's the process. You take rows times columns. And if the number of columns here didn't match the number of rows, the numbers wouldn't match up. So that's why this dimension has to equal this one. So I put B times A here. Well, B times A wouldn't work, because when I take 3, 2, and I turn it and try and go down this column, I have 2 things here and 3 there. I wouldn't even know where to put them. Should I do the first 2 or the second 2? It wouldn't make any sense. So that multiplication is undefined. So matrix multiplication, you'll need to practice this a little bit, and you can refer back to this picture here that shows the details and steps. And of course, Wolfram will do it for you as well, and so will your calculator. Now another matrix I want to identify is the identity matrix. Identity matrix is like the identity for multiplication. If I multiply the number 1 times any other number, I get the same answer. And that's what happens when you multiply by an identity matrix. Identity matrix is 1, 0, 0, 1. In fact, it always looks like this. 1 down the diagonals and zeros everywhere else. And it'll be whatever dimension you need. It's always a square matrix. But you may need a 3 by 3 identity, then it would be 3 1s and zeros everywhere else. So to see why this would give me the same thing, let's see when I multiply it times 3, 2, negative 1, 5. I get 1 times 3 and 0 times negative 1. So 1 times 3 is 0. 1 times 3 is 3 plus 0 gives me 3. I get the 3 back. 1 times 2 is 2. 0 times 5 is 0, so I get 2. 0 times 3 is 0. 1 times negative 1, I get the negative 1 back, and the same for the 5. So when I multiply this identity, nothing changes. So here is a generic identity matrix. All 1s down the diagonals, 0 anywhere else. This could be any dimension n. Don't usually write identity 3 by 3 or 4 by 4 because they're always the same. So identity 5 would tell me it's 5 by 5 matrix. So that's the pattern. 1s down the diagonal, 0s everywhere else. Now one other special matrix I want to define for us is the inverse matrix. Just like the multiplicative inverse of 3 would be 1/3, because 3 times 1/3 equals 1, the multiplicative identity, we do the same with matrices. An inverse matrix times the original matrix gets you the identity matrix, which is sort of taking our matrix place for 1. Now, we'll find inverse matrices by using either Wolfram or the calculator, so we're not really going to find these by hand in this course, but we need to know what an inverse matrix is. It's a matrix that when you multiply it times the original, you get the identity matrix.